I think we're alive. Okay. 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 I'm gonna hit the thing, and we're doing it. Hi. Hello. Hello. Oh boy. What a morning. I've got a new audio interface. I've got a new setup. A lot of things didn't work, but I think we are back, and I think we're ready to write some amazing code. So, hi, I'm Tom. I talk about code. Today we're writing more Rust. We're diving back into my 16-bit virtual machine. I thought I was done with the weeds, with the little wiring macro stuff, but I'm going to take that as a starting point, and I'm going to work on the ISA, because as I've started to try and write code for the virtual machine, I've realized that the instructions and the way the machine was working, being very stack-based, it kind of sucked. So I'm going to write a better ISA with better ergonomics that makes it easier to do things. And I think I've been a little bit clever, okay? Because on Sunday, I actually caught a train out to buy my new audio interface. I can't hold it up for the camera because it's plugged in. But I caught a train out to get one cheap secondhand. I was on a train for about 2 hours. So I had time to do this. This is a new ISA with a bunch of notes about how things are going to work. A bit of example code I was trying to scribble out. So I've got a plan, okay? And the plan is a lot better. So let's jump over to the code. And let's, like we've got this instruction format. It was a little bit limiting. It was a little bit too simple. So I'm going to get rid of this. It's gone. Okay, we're going to have two types of instruction in my machine. This is the future going forward. And I've taken some inspiration here from the Elements of Computer Systems book, the NAND to Tetris book. Okay, but we're going to split our instruction set into two distinct things. The first type of instruction is going to be an immediate instruction, right? A way of loading data directly into a register. So the way we're going to write these out, right? 0 is a literal 0, like a 0 bit in this instruction. At 3 R's is going to be a register selector. We're going to have 8 registers, 3 bits of register data. So 3 bits to select a register, and then we're going to have 12 bits of literal integer goodness, okay? So this is a way of loading just 12 bits directly into a register, smashing it in there. This is something that was a little bit lacking in the current instruction set that was there. We're still going to take this a little bit further. Well, a little bit lacking. I don't know. It wasn't quite as elegant as I wanted it to be. The fact that we were dedicating a whole 4 bits to register selection and we only had 8 registers meant that we were wasting some space. We couldn't be quite as nice as we could here. So this is our first type of instruction. We're also going to have a type B instruction, okay? Well, we kind of have 2 types within type B. I'm going to call them all type B for now. These start with a 1, okay? And then we have a register, like the other instruction. Then we have another register, which I'll call S, because I can't exactly write R0 and R1 as I do when I'm handwriting, so we'll call it S. So 3 bits of one register, 3 bits of a second register, 5 bits of, I'm going to call this A for action. I thought about writing O here, but that looks a little bit too similar to a 0. So we're going to say A for action instead of O for op. And then 4 bits, this is like our destination or maybe some kind of extra parameter. So let me give you an example of an instruction in this format, because this is a much more dense format. There's a lot more going on here. Encoding and decoding these instructions is going to be a lot more fiddly, okay? So let me give you an example instruction. Let's take the add instruction, okay? Where the action is going to be 0. Now let's assume and B equals 2. So we're going to have our 2 registers, right? So let's write an instruction that says A equals A plus B. Currently, register A has index 0. In the future, like from right now going forward, it's going to have index 1. So let's write an example instruction in this format. 1. So let me spell it out first as well. So this is going to be saying the register that we specify in the destination bits is equal to the register that is spelled out by the R bits plus the register that is spelled out by the S bits. So 1, we're adding A and B. We're gonna store the result in there. We'll say A equals A plus B. Okay, so 0, 0, 1, 0, 0, 2, 0, 0, 0, 0, 0, 0, 0, 0, 1. Right? It would look like that. No, it wouldn't. What am I saying? I did this in hex instead of bits. Let me do that. Let me do that actually correctly. 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. That let's do it properly. Oh man, that was funny. That was like halfway between writing it in hex and halfway between writing it in binary. Okay. Now, one of the big changes is going to be that one of our 8 registers, instead of the flags register, is going to be a 0 register. Okay, so the register 0 is always going to be equal to 0. And it's going to have index 0. So 0 equals 0. Okay, so reg 0 is always equal to 0. You can't set anything to it. And this is inspired by Risk. And this means that we could write reg A equals reg B plus reg 0. Right? Or to encode it as an instruction, 0, 0, 1. Well, let's say 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, right? 0, 0, 0, 1, 1, 0. Let's do it properly. So A is 0 plus B. In other words, move B into A. This is the Risk way of doing this kind of thing. Also, anyone rolling into chat right now, please give me a sound check. I would love to know if I sound okay, because this is a new audio interface, and I can definitely twiddle the knobs if we need to fix anything. Yes, it looks like it's all coming through. It all looks okay, but I'm nervous. Okay, so this is how we're going to encode instructions. You might be looking at this and you might be thinking, wow, this is a lot more complicated. And you're right. The macros are going to have to do a little bit more fiddly stuff, but it's fine. I think all the complicated stuff is already handled, but this is going to be another stream of diving into macros and messing around with that. Zymus says I sound fine. Thank you, Zymus. Perfect. Wow, love it. Love it. Let's give another example of an instruction. Okay, let's say stack. And let's say in our stack instruction, action is going to be FF, maybe. No, we don't have that many bits. Let's say it's, oh no, we do have that many bits. Yeah, let's say FF. No, wait, no, we don't have that many bits. We have, let's say OF. That's okay. Or just F. So all of our stack instructions are going to live under one set of action bits, and they're going to be, the action is going to be determined by the D. Now, using the A register and A here, this is a little bit confusing. This is a little bit overloaded, but just you know, when we're talking about registers, A means something. When we're talking about the actual encoding of an instruction, it means these 5 bits. So let's say we want a push instruction, right? Then we're going to have D equal to 0. And so that, if we want to maybe say push whatever's in register A, we'd say 0. We start with a 1 because it's this type of instruction. We specify register A. We specify the stack pointer as register, because we now have room in our instructions to actually take a register in. So you would probably always work with the stack pointer register, but you can choose which register your stack pointer register is out of any of the 16. Maybe that'll allow for some fun creative things, maybe not. And then we say 0, 1, 2, 3, 4, and then 0, 0, 0, 0. It would be encoded like this. If we want to maybe have a pop instruction where D equals 1, and we want to say pop into B, it would look like this. So we can encode these bits. Hopefully you get the impression that I know what I'm doing. We have these masks that shouldn't be hard to work with. And let's see, we're going to gut literally this entire thing, right? We're not even going to have a NOP instruction anymore. NOP is now just going to be this. Right? Because this instruction will just be add 0, like 0 equals 0 plus 0. In other words, do nothing. So we don't even need an explicit NOP anymore. What this means is we're going to have a very dense ISA with very specific instructions that can do a lot of different things. And then maybe on top of that, we write a more restrictive assembly language, for example, that has a pop and a push instruction, that can compile down into this weird thing where you can specify whatever register you want as a stack pointer, but you probably won't actually do that in practice. But it's there, right? The ISA will support it. Maybe I should really get a tablet or something so I can draw pictures while I'm talking about this. That was a lot of words. I hope my text file bashing is enough to follow. But we're pretty much going to come in here and just delete everything. I'm not... Yeah, actually, let's do it. Let's do that. Okay, so... Ah, crap, I have... Oops. Okay, well, let's just commit everything as I had it last stream. What's... Whatever I was doing last stream. I think this is okay. I don't think we made too many fundamental changes. Because bin ASM. So we changed how the assembler worked, and then we wrote new things. I don't think we actually delved in to the deep inner workings. I think we are safe to ignore this branch for a minute. And then we have this op stuff we just changed. Yeah, excellent. Okay, perfect. So we're going to put our preprocessor macro assembler aside for a moment. We're going to check out smart ISA. Okay. Cool. We're gonna get rid of every instruction. We're gonna get rid of every single instruction, except not for now because we want an example. And we're gonna write out the entire ISA as I have it in front of me. So this is gonna be add, which operates on 3 registers. We're gonna have a subtract, which also operates on 3 registers. And that's gonna be opcode 1. What else do we have? We have load and store. Now, load and store, yeah, perfect. Which will also take 3 registers, right? So opcode 0x2. This is gonna say let's say a register equals RAM and this can even be an OR, I guess. But, you know, basically, we're going to build a 32-bit address out of these 2 registers and read that from RAM, which was always kind of my plan for how this machine would go, right? You know, we would have this way of combining 16-bit registers to do bigger reads. And this could just be the 0 register, right? Maybe you're only ever reading from this like 0 page, these 16 bits, and that's fine. But the option is there to generate much, much bigger addresses. We're going to have a store, which is going to take a register. And this is going to be the same thing, right? RAM R1 or R2. Right, where we build this address and we store the thing. And so we use the same registers for building the address to keep consistency, even though we kind of like swapped where this, you know, maybe it would be logical to some people to use a different register here, but we want the addressing registers to stay consistent. That's how we're going to get more efficiency out of our instructions. Okay, what else do we have? We're going to have test. Now, test is going to be interesting because test is going to take something special. God, I need to like prop this up somewhere where I can see it and talk into the microphone. I also need to work out how to read my handwriting. Okay, so this takes a register. It takes a register, and it's also going to take a test op, which is going to be a special thing specific to a test instruction that we'll know how to encode and decode, and our macros will know how to deal with, but we just need to define it. We're going to have an add if instruction. And this is going to take a register. This is also going to take a 4-bit literal. So maybe I'll call it nibble. Maybe I'll just call it nibble. I don't need the word literal. Now, yeah. So add if is going to be used in a fun way. We'll see how that comes out. We're going to have a branch immediate instruction, which is tied to a specific register. Hold on, I need to revise my notes because my handwriting is really bad. I mean, I don't know about you guys, right? But like, this is hard to make sense of. It's hard. It's like doing archaeology on my own brain from less than 2 days ago. Okay. I just had a Discord comment saying ambitious start to my stream, which is fantastic. So what is this? What is this thing I've written? I've written is that D? It is. Okay. So, now, if we take all of our bits, if we take R0, R1, so if we take R, S, and D, we can combine these into 4, 7, 11 bits, 10 bits of constant, okay? So this branch, this is going to be an instruction that just, I guess we should call it jump, right? Jump. And it's going to take a literal 10-bit, maybe, which we'll know how to encode, right? If we want a 10-bit literal, there's only one way to encode that, given this. There's only one spot we can fit a 10-bit literal. So we'll know what to do with this. We're going to have shift left. You don't need logical on shift left. It's just a shift left, which is going to take a register, and a nibble. We're going to have 2 shift rights. We're going to have a logical and an arithmetic. One of these does sign extension, one does not. We're going to have... that's fine. We're going to have... yes. What was I doing? What is it? I've skipped one of these instructions because it doesn't make sense. We're going to have a generic stack instruction, which is going to take, similarly to our test, it's going to take a register, and it's going to take a stack op, which is going to tell it which kind of thing it's doing, and we'll know how to encode that into the D field. We will have... Oh yeah, we want this as well. We're going to have a special load stack offset instruction, which is going to take 2 registers and a nibble. And this is just going to be for loading from an offset in the stack. It'll be useful for when doing calling conventions. I think let's move our arithmetic all up into one spot because... that's going to be useful because we're going to have more. We're actually going to also have add immediate, which is going to take a register. It's going to take literal 7-bit, which is like a literal 10-bit, but instead of taking all of these register fields, we're only going to use S and D. R is going to be kept as a destination. So we get 7 bits that we can that we can know how to encode and decode, right? Anytime we see literal 7-bit, we know exactly which 7 bits they have to come from. When we see literal 10-bit, we know exactly which 10 bits they have to come from. It's consistent. There will be a signed and an unsigned variant of this, because sometimes you want to subtract one instead of just adding, 1, 2, 3, 4, 5. Then we're also going to have a system, which is going to take a register, which might as well take... Actually, no, it's going to take 2 registers and a nibble. Because I thought it would be fun rather than... well, it might be fun to be able to call the first 16 system operations that we hook into our machine directly in the instruction rather than having to override a register for it. Anyway, this is all getting very technical, but this is an instruction set, and this might look like absolute nonsense, but it's going to come together in a really cool way. Okay. What else do we need? Now you might be wondering as well, if I put all of our arithmetic together, why is addif down here? That's because addif is basically a branch instruction. It's just a branch instruction that does not specifically operate on the program counter. Why would you do this? Good question. 7, 8, 9, A, B, C, D, E. So this actually all fits in 4 bits, hilariously, but we've got this extra bit just in case we want to add more instructions. We've got a whole... We haven't even used half of our instruction space yet, and there are a few more instructions here that I might get to at some point, but we will see. So we need to make these types as well. So what types do we have? We're going to have to make a struct literal 7-bit. This is gonna consist of... Now, the best way to do this... I mean, there are 2 ways to do it. One is to actually store the 2-bit patterns separately. Also, is there a good way... Does Rust let you define restricted types? Like types that are smaller? Does it let us do this? I don't think it does. I don't think it's one of these languages, so that's okay. So let's make this a U8, I guess. And we'll just understand how to mask it, but also... Okay, we got to think about what this... I guess... we probably want a function that's something like maskable, which will give us back a U16. That's not the character I wanted. Right, something that'll give us a thing that we can OR together with the rest of an instruction. So for example, in the case of a literal 7-bit, it's the bottom 4 bits, and then these 3 bits. So that would be, we need to also reference ourself. So this would give us self.value and f. We need to cast this up to a U16. Now, what is the mask for these 3 bits? It's 00. What's this number? 1110. That is E. So 00 E00. Cool. So this, what we're saying is, if we have a 7-bit literal that's encoded in the instruction, how do we get this back into the format that we can like mask with the rest of an instruction. Where do these numbers come and go from? Oh boy. Oh boy. Okay. 7. This should be a capital B. This should really be a capital B. It'll be the same thing with the nibble. It'll be the same thing with the 10-bit literal. This should probably be like a trait that we implement. Maybe. It's hard because with these registers, we're not going to be able to do it. We're just going to have to know. We're going to have to deal with these a bit more manually. But that is okay. As long as the rest of the more exotic bits are not too weird, I guess. Okay. Let's make a trait for this. Let's make a trait that's called trait and we'll do the thing we're doing here. So turn this part of an instruction into something that we can mask with the rest of a 16-bit instruction. Impl instruction part for literal 7-bit. Cool. All right, what else do we need to do this for? We need to do this for literal 10-bit. Right, so just doing the plumbing, right? What are the parts of these instructions? How do we model them in Rust? You know, how do we use the tools in Rust to model them? Man, the C programmer in me just always finds ways to come out. This is also a struct. But yeah, how do we use the tools Rust gives us to model these types in a sensible way? How do we make sure that we do as little work in these macros as possible? Because they are pretty gross. But this is actually just going to be the same thing. It's just going to have an extra self.value. We're going to AND it with. So in this case, it's 0007. No, sorry, that's backwards. Hex 7000. So it's not the top bit, the 3 bits following that, and then the rest of it 0 in our 16-bit word as U16. Beautiful. Okay, now we're gonna pub enum. What do we have? We have test op, and we have stack op. Cool. So our test op is gonna be the different ways we can compare things. So for example, equal, not equal, less than, greater than. Actually, given that we take 2 registers, I think we just need less than and less than equal, because then we can always just swap the registers. That's fine. Equal, not equal, less than equal. We're gonna have a test called, I guess, both 0. Right, which is true only if A equals 0 and B equals 0. I think that's a useful thing to test. Let's say both non-zero. This would also then, because we have a 0 register, you could then use this to check if one register is 0, because you could always use, let's say, either non-zero. Right, we can just add tests here. We have 16, so 1, 2, 3, 4, 5, 6, 7. So we've got a lot of space that we could expand into here. Stack ops, similarly, we're going to have push, pop, push, peek, swap, dupe, rotate. Right, with just a bunch of stuff we can do on the stack. We're gonna make these both represented by U8s. We also want to derive debug, just because you might as well. Okay, now impl for test op. Right, so just making sure again, you know, modeling this stuff sensibly. We want to get rid of the pub here. This is actually an error. You don't do this with traits. As mask gives us back a U16, and in this case it's actually going to be very simple. I don't know how I just collapsed that. That was an accident. That was a very cool command, but I don't know how I did it. Thanks, Vim. Okay, self as U8. I guess self as U16. And then we just mask out the lower 4 bits, because they're just these 4 bits. So the bottom 4 bits, it's not that complicated. Excellent, excellent. It's going to be the same thing for the stack op. It's going to be literally the same implementation. Copy and paste. Awesome, awesome. Okay. We've gutted everything. What other type do we need? We need a nibble. We need a nibble. And a nibble is also going to be extremely simple. For nibble. Excellent. Cool. We maybe also want to validate that these are within their bounds. I don't know. That might be a good idea as well, I guess. And then I guess, yeah, we also want to be able to, do the opposite of as mask, right? Read the value out from an instruction. So if we're a 7-bit literal, did I finish doing the nibble? Did I finish my nibble? I did, good. I forgot what I was doing for a second there. I had a little brain moment. Okay, so the other thing then, yeah, we need to be able to do is from instruction like maybe this should be into U16 and try from U16. But I think there are 2 things that I've really had time to think about. One is that this seems to have more meaning to me, right? Like we're specifically defining how this thing works as part of an instruction. It's not a U16, it's not its own number. But then also... Maybe this should just be a try from. The other thing is, like, this can't fail, right? As long as this is a U16, there's no fail condition for masking this out. So I think that's okay. I think this function signature makes more sense. We can't fail. There's nothing that can go wrong here. That said, here there probably is, because the value could be invalid, but I think we might handle validation separately. Okay, that's one to think about. That's one for consideration, but not for right now. I just want to get something working, because I'm starting to write an amount of code where I'm nervous that I can't actually test it, right? That's always hard. That's always hard. Okay. So from instruction, self.value equals, no, sorry, we want to give back a self with a value that is it's the instruction or, and this needs to be downcast to a U8, otherwise it's going to yell at me. Ins and 0xEOO. Now these are the upper 3 bits, so this needs to get right shifted down by 8, but then back left by 3, so it's downshifted by 5, right? Because, no wait, hold on, 1, 2, 3, no, by 4. Yeah, by 5, because we need to get rid of this 0 and the 0 here. So it's 5 bits we need to shift. As U8. And I'm just going to gratuitously bracket and let Rust tell me when that's too much. Okay? Cool. So now we can build a self from an instruction. We're going to do the same thing with the 10-bit literal. It's going to look very similar, but then we're going to have this extra bit as well, which is going to take even more shifting. We're going to have to be very, very clever. We're going to have to use our brains, which, you know, it's always a struggle in the mornings. Okay, so this is hex 7000. Now we need to right shift this. Okay, so right shift 12 and then left shift. This is the top 3 bits of a 10-bit literal. The top 3 bits of a 10-bit literal. So it's right shift 12, left shift 7. So that is also just a right shift by 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Yeah, so this bottom bit becomes the like 8-0 bit, if that makes sense. Except these are now U16s. Cool. Cool. Okay, yeah, we can do that. We can make that work. Now. This one probably wants a try from instance, right? Okay. This one probably wants a try from. What do I do at the moment for registers? Yeah. We're going to do the same thing. We're going to do the same kind of thing here. Okay. So and let's just check my docs. Rust try from T. Type error equals string, just so we have something to work with. Try from sorry, it's a result. Excellent. Okay, so value. How did I do this in register, sorry? It's this silly thing, x if x equals test op as U16. It's like this, yeah. Which is just the worst way of writing things, but sure. EQ, NEQ, we're gonna have LT, we're gonna have LTE, we're gonna have both 0, we're gonna have both non-zero, we're gonna have either non-zero. And then we're gonna have error beautiful. Okay. Yeah, but when we have an instruction, so we're just going to unwrap, I guess. This is the important thing. From instruction Wait, can you put this in a trait? I don't think you... I'm doubting whether this is actually valid in a trait. Maybe this actually needs to take a mute self, which is okay. We can do that. But I guess I'll just keep writing for now and we'll find out. It's the cost of change is low. So let's say, nah, I don't think we can do this. Oh, but how does this even work then? Because we want to say, try from ins unwrap, basically. And what do we get? Closing delimiter possibly meant for this. Unclosed delimiter. That makes sense. Okay, now we got some stuff. Now we got some stuff. Expected one of. Anonymous parameters are removed. Give it a parameter. Oh, okay, sorry, we can't. Wow, I didn't realize we had to do that. Okay, well, that is kind of good, maybe. Our macro panicked. Something has changed. Okay, I'm just gonna run to the bathroom real quick, and then we will dig into macro land and work out what's going on, and hopefully fix it back in a second. Ooh, that wasn't the right scene. There we go. All right, let's go. Home stretch. Home stretch. We're going to dive into this macro. And this is good, right? It actually gives us the correct message. Our macros for encoding and decoding these instructions don't know what to do with 3 registers because they only know the old instruction format. Also, I guess I should add the actual immediate instruction. Let's maybe just call it im, which is going to take 1 register, and it's going to take a literal... Damn, there's another one. I forgot this. But this doesn't really have an opcode like other instructions do. So maybe we'll just give this opcode 0 as well. Sure. Or maybe, I don't know. It doesn't matter what we put here. Literally does not matter. Okay. Is this going to actually break a significant amount of the macro? Maybe. So what are our macro types? What are our macro types? Yeah. Fields unnamed. So fields register. So this is where we need to dig in, right? So we no longer have these. This is good. And all these things now live together, which is also good. So every instruction that takes 2 registers. I guess we need a special case for our immediate. When we actually build, yeah, we match on the op. We match on the op, which is no longer really possible. So we're gonna have to change how this works. We're gonna need an if statement at the start here, and early out, and then match on op. We're gonna need to say like, let's start with the encoding. Okay, so let's go get. We need to finish our homework in op. We need to just finish this one more really freaking boring thing. And this still isn't completely done, by the way, but we're going to copy literal 10-bit, and we're going to make literal 12-bit. Actually, no, I don't think we are. I don't think this is a proper instruction like the other. Okay, I'm going to be lazy. I'm going to be lazy because I'm sick of how bloated this is feeling. And I'm just going to put a U16 here. And we're going to call this literal. And because it just puts a number in a register, a literal number. Immediate, literal. I guess we'll call it immediate. We'll call it immediate. Okay. I'm going to stop faffing around. This is too much. This is too much. Oh, we should also add toString and fromString for these. Oh no. Can we derive these automatically? Maybe. Okay. So, man, I think this is a glasses on day. I just have this microphone in the way of my screen, which is a little bit tricky. Instruction. So if the top bit of the instruction is set, match type B, else we want to grab the register from the next 3 bits. So let register equal. So this is the distinction, between like this bit being 0 means we're going to grab these 3 bits and the rest is a literal. This being 1 means we do the actual complicated decoding. So this is where we'll say let op equals ins. And this is where we want these middle 5 bits. So this mask is 1F0. 1F0. If you don't know how I'm building these masks, you just get good at it when you look at enough hex. Doing PlayStation 2 Homebrew really trained me. In this. We then need to right shift this because it's by 4 because there's 4 bits of trash at the end, and then we just get a nice 8-bit number, right? Well, a nice 5-bit number that we put inside a U8, and then we say match op and do all of this other stuff. Excellent. Okay, here we go. Why are these? I have a single space that's messing up my indenting. Yeah, cool. Okay, I thought that looked weird. So if that first bit's 0, we want to get the register, and again, we're going to have to build one of these masks. We want to mask out these 3 bits. So that's hex 7000. Right shift by 12 as U8. 8, I guess. And then we want to say, oh, why is my indentation messed up? Oh, this indentation's messed up. It's all one space off. That was one too many. Okay, here we go. There we go. I hate it when you can see your indentations unbalanced and you just can't work it out. You just can't crack it. Okay, register is this. Register bits. It's actually probably, what's the, is it Rust option, is it or? Okay, or on okay, so we've got a register, and then we just want to return its instruction immediate with our register, and the instruction, the lower 12 bits masked out. Okay, holy crap. There we go, there we go, there we go. That is beautiful. That is absolutely beautiful. So encode U16 encodings, that's fine. We have a decodings, that's fine. Well, this one just has a special case, but the others it won't have a special case for. This is the only place where we need this special case because we match on the opcode. Nowhere else do we match like that. Everything else is just part of the instruction. Okay, so fields, toString fields, from string, yeah. So from string is going to be a bit broken for a while, but that's okay. Okay, so these no longer exist, but we'll keep them there for a second just for posterity. Let's dig into the easiest case, the one where we have 3 registers, okay? So now we have 3 registers. And this is a little bit tougher because of where the opcode gets encoded. Oh dear. Oh dear. Okay. So this is just suddenly a little bit messier. How do we encode this as U16? So the first thing is opcode value as U16. This no longer goes in these lower bits. We have to shift it to the right by the left by 4. And then we OR that with, let's do it this way, OR that with the register as a U16. Now just the lower 3 bits of this number. And we left shift this. So the first register is always these top 3 bits. So we left shift this by 4. We left shift this by 12. The second one we left shift by 4, 8, 9. And the last one we don't left shift at all, that's our destination. And so one of these sets of parentheses is now redundant. Holy crap. Okay, there we go. This is how we encode an instruction with 3 registers now. Decoding is going to be the same thing, but we're going to have to, again, we have a 3rd register. And again, we're going to do this masking. So the first register is in the lower 3 bits here. These 3 bits. Then it's going to be E, O, O. And then it's just going to be the bottom 4, okay? So this has to get right shifted by 12. This has to get right shifted by 9, the inverses of this. And then this doesn't have to get left shifted at all. Indeed, it doesn't even need the brackets. Okay. And now we also need to do this a 3rd time. Excellent. And so again, yeah, like reading this from a string is very easy. Reading this to a string, to and from a string, like this is the easiest this is going to be. This is the easiest that this is going to be. Stringify name. Excellent. Okay. So what other types do we have in op? That was the easy one. That was the one that was most similar to what we were already doing, but also in a way it was very tricky. This one doesn't count. Well, I guess it does. Encodings. Yeah, so we just don't have a decoding for this first instruction. We'll get back to this one. So register literal 7-bit. So if we have a register, let's just chuck it in here, literal 7-bit. Okay, this is going to be very similar. This is going to be very, very similar to other things we're doing. So this encoding isn't hard. We're going to have a register, we're going to have a literal. Let's just put this here so that it's a little bit easier to deal with. Opcode value. So this is okay. Now we just need to properly jiggle the opcode value around. Opcode value is U16. Left shift it by 4. That's all we got to do. And then this gets ORed with the register, which gets left shifted by 12 because it's the first register. And then this also just gets ORed with the literal dot as mask. Isn't that nice? Isn't that kind of nice? We don't have to mess around with this stuff too much. And actually, maybe we should add to the register, right? Maybe we should just be able to say r.asMask first. Like have asMask first, you know, asMask second. Like make this part of the register so that this encoding, but also should the very nitty-gritty details of this encoding infiltrate this otherwise quite clean file. I guess it puts it in a little blob. I don't know. As it stands, all of the encoding and decoding logic lives here, and I'm kind of okay with that. I'm kind of okay with that. Except it doesn't anymore, right? Because we just put a bunch of it into op. Okay, nah, screw it. Register, you're getting these functions. as mask first, u16, and this is going to give us, what did I just do? This. Okay, so self as u16, and that's it. That's what we need. As mask second, this is left shifted by 9 as we learned just before, and then the last one is left shifted not at all. Excellent, beautiful, beautiful. What time is it? Okay, we're tracking okay for time. As mask second, and so then do we also probably need pub fn from mask or from instruction first? Where we grab the field from an instruction, we say ins and 7000 as u8, we say self from u8 unwrap, because it shouldn't fail. It really shouldn't. There's no way it really, no. Oh, okay, that's not strictly true. But we're gonna just unwrap for now because we need to do something. And then we're also gonna, this one is the one that can fail because we're actually potentially reading out of range. Okay. So instruction second, this one is E1000. This needs a shift as well, sorry. This needs, of course, to be right shifted by 12 so that it's in the correct, the bits are in the correct spot to be treated as a U8. This one needs to be right shifted by 9. And then this one just does not need to be shifted at all. Let's do this in a way where a whole bit is ignored and there's no death condition, there's no failure condition. Because that's how we're masking it as well. Okay, cool. So now we can do this better. We can do this way better. As mask first, as a mask. Let's go down into all the register stuff we just wrote and make this actually good. R1.as mask first, R2.as mask second, cool. That's a bit nicer. We can also do this register from second, third. Okay, cool. That's just a lot nicer. That's one less thing to worry about. Oh, and this okay, let's not even unwrap. Let's return the option because that we're already handling it. We might as well keep the code that was handling this before. The thing I just kind of overlooked, I changed this, but I didn't realize this actually gave us back a register, so this bit now isn't needed anymore. So what we probably want to say is reg1 is this dot okr, right? Does that make sense? Instead of doing this from instead of doing this in 2 steps, we're now just going to do it in 1 from we no longer get a good error, but I will accept that. We can do a better error. We can do a better error later on. That's workable. Okay, beautiful. That's cleaner. We're getting cleaner all the time. Cleaner all the time. Register. Cool. Now the decoding as well. Okay, so we've got a register. Then we also need to say let lit equals from instruction. And then we return hold on, how did I do this? Self name, yeah, self name lit, right? So, except does it need to be an okay? It needs to be an okay. It needs to be wrapped up nice and safe. God, I was considering doing this off stream, but I think this is way more fun on stream. Subjecting you all to this poor, depraved journey into madness. Okay, so this is a little bit janky, but that's okay. We can deal with it, because then we just need this. Okay, cool. So that's 2 of our instruction formats down. Only a few to go. So we have register, we have this one. We need register nibble. We need register test stop. We need register nibble. We need literal 10-bit. We need register stack up. Okay, so there's still a bit of work to do. Let's do register nibble, and then maybe comment some stuff out and see. Actually, let's start commenting things out now and see if it builds. Actually, no, let's do this one as well, because this one's kind of important. Because if I don't do this right now, I'm gonna feel very silly later. Let's get rid of the instructions that just had these numbers. That is not needed anymore. These 2 examples are enough to go off of. Okay, so let's actually put it first, because this one's weird. Let's go register U16. Encodings. So encoding it is really easy. We're just not gonna have a decoding here. Encodings, register number, oh, this also needs these also all need this, don't they? They need this top bit set. Is this something I should do maybe here? I think that feels better, right? I don't want to have to try from U16. Sorry, those are decodings. That's fine. Encodings. Nah, look, it should It's kind of hard, right? Because every instruction is just going to, every format is just going to need to remember to have this, but I guess that's okay. This top bit needs to be set. This is part of our format, but am I going to forget to set this top bit? Because I had already with this work. I guess we'll just have good tests that catch it eventually. I'll have some tests eventually, maybe. Cool, so when we encode this instruction, all it is the right. So these instructions, right? These type A instructions that are just one 12-bit literal and one register and 0. It's just this. It is really just this. This is all we have to do to encode it. This is all we have to do. When we're converting this format into a string, all we do, let's just copy gratuitously from other places, name rm, that is perfect. And what else have we got? From stir, I guess we can copy that as well, because it's just a number. It is just a number. This is, I really probably need to do like the radix pass number or something, but we'll think about that a little bit. I guess we have to do it here anyway. Radix parse. Well, there's a helper for this, isn't there? I wrote one. Where is my helper? Parse numeric signed. Parse numeric. But it only gives back a U8. See, I just don't know if parse numeric will be used anymore. Maybe I just need to make it a U16. Oh yeah, and this is an I16. That's okay. That is perfectly okay. Okay. U16. And then I16 from radix. Okay. Parse numeric. So instruction, parse numeric. Okay, I think we're good. I think we're good. I think this checks out. Okay, so let's go in here, let's comment out some lines, and let's see what bloody happens. I'm very nervous. What if I just comment out... well, I did literal 7-bit, so let's do this. Let's just comment everything out to here. And this is going to be so upset with me. Unclosed delimiter. That checks out. Okay, there's going to be so many errors. There's going to be so many errors. Unreachable pattern. I mean, how did that build? Really, how did that build? Oh, because I was in the other package. That makes sense. Okay. Expected blah, 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 found blah. Missing from instruction. That checks out. Casting stack op as U16 is invalid because it's a reference, not a thing. We just need to put a star there, I think. This derived macro cannot. Literal 7b is not implemented. I just need to add debug. That is fine. That's not hard to do. Literal 7-bit doesn't implement display because we don't implement debug. Once we implement debug, I think we get... Oh no, we don't, but I'll just debug print it instead. That's fine. Cannot be formatted with the default formatter, blah, blah, blah. Tuple variant defined here. An argument type register is missing. Okay. So that one I do know how to fix. This one, when we have 3 registers, one of the instances of constructing self-name seems to only have, yeah, here, this. Okay, so that was one of the errors. That was one of them. Op RS 134. That's not the right... Okay, so we've got a syntax error, and it's really, really hard to track these down. Really, really hard to track these down. Unfortunately, I might even have to leave this one dangling, because I've got to go have a shower and do some work before my singing lesson. But this has been the fun start of a very big refactor. I might tackle some of this really tedious stuff off camera, save you some of the pain, and then when we come back, we'll start writing code against this new, improved instruction set and doing cool things with this computer, because it's about time. I've spent a lot of time messing around with the rusty parts and down in the weeds. But this has been fun. Hopefully, I am going to be back streaming more regularly. My audio interface dramas were unfortunate. You can actually see the old one is on my desk in the soldering station over there. You can kind of... Let me just grab it real quick. This is the state of my old audio interface, okay? I attempted to solder a USB... I won't get too close to the soldering, it's a really bad job. I attempted to solder a USB cable directly onto the base because I was having issues desoldering the broken USB-B port. And this kind of worked. I got power over USB, but I just wasn't getting the data signal properly. I think it was just a bad solder job. So I went and bought a new one. And maybe I can fix this still and I'll have a backup. It's kind of hilarious having USB cable soldered directly onto it. But I'm going to keep playing with it and see what we can do. So... I actually recorded all the footage of me messing around with it as well, so I might make a little video talking about my adventures, especially if I ever fix it. So, thank you very much for tuning in. I'm Tom, and I will catch you all next time.